discharge the heat of the storage tank at a required temperature level. Imagine a storage tank which is cold, just 20 degrees of water temperature, and you fill that tank with water of a temperature level of 60 degrees, but you fill it just to the half, and then you get a mixing inside the tank. Then you have an average temperature just of 14 degrees. If you would like to use that temperature to drive a floor heating system, that should be fine. But if you would like to take the temperature to operate radiators, it's much too cold and you do not get enough power out of the system. So it would be more helpful to have half of the energy on a higher temperature level. So that's a very important thing, to keep the temperature level. And another thing we are not talking about today, but what is also can be quite important, is the hydraulic decoupling of the generator or the producer of heat and the consumer. What are the fields of application for storage tanks? In general, we use storage tanks if we have a mismatch of heat supply and heat demand. That is, for example, in all kinds of solar systems. But because the sun is usually shining during daytime, but when do you want to have a hot shower? Most times either in the evening or in the early morning. So you have to store the heat somehow. But another application for storage tank systems is domestic hot water systems to reduce the peak load. Do you have an idea how much power you need to heat a shower? It's about 20 kilowatt of power you need. Now if you have 2 showers within one house, you need a capacity of about 40 kilowatt to drive that or to heat that shower at the same time. But the heating system for one family house nowadays needs about 5 to 10 kilowatt just for the heating. So you could not power 2 showers with these small heaters, and for that reason you have to store the heat somewhere. Another thing is we use storage tanks also in hot water heating systems to reduce the cycle frequency of the heating generators. That means the switch on and off of the heat generator. Especially, for example, combined heat and power stations, CHPs, it's not good for them if they have to start too often. That reduces lifetimes very much. Another thing is some of the heat generators have a lower efficiency under part load conditions. And so you should not run them under part load conditions because you lower the efficiency. You run them under nominal load conditions and just switch them on and off. And therefore you have to store the energy. Most things I'm going to explain you here, I'm dealing with heating technology, but all the ideas can be transferred to cooling systems quite easily. The start point of our investigations was an unsatisfied operator of a combined heat and power station. He was unsatisfied insofar that the CHP had too many starts a day, and he was worrying that the engine is not running for a long time. In this slide, we see the hydraulic scheme of the plant. On the left-hand side, we have the CHP with a thermal power output of 10 kilowatt. And on the right-hand side, and just the supply temperature of the CHP is 90 degrees. On the right-hand side, we have the consumer. The consumer in that case was just a radiator heating system in more family houses. And the supply temperature of the consumer was designed by 70 degrees, and the return temperature was designed by 50 degrees. There was a hydraulic, a thermal storage tank inserted as a hydraulic switch or a hydraulic separator with a storage capacity or with a storage volume of 1,000 liters. And the question now is, how much energy can be stored in that hydraulic tank? It can be, the ideal storage capacity can be calculated quite easy. You just multiply the mass of the storage tank, 1,000 kilos, that means the mass of the water, multiply it with the specific heat capacity of the water, and multiply it with the temperature difference between charging and the discharging point. The question now is, what is the maximum temperature you can charge the tank? Under these conditions, we have a supply temperature of CHP of 90 degrees. So the theoretical maximum temperature of the storage tank would be 90 degrees. Next question is, what is the lowest temperature of discharging? The lowest temperature is the return temperature from the consumer, which is 50 degrees. Though we have a temperature difference between charging and discharging of 40 degrees. And that gives us, if we write it in the equation, 1,000 kilogram multiplied with 4.2 kilojoule per kilogram Kelvin, multiplied with 14 Kelvin. So we get a storage capacity here by 47 kilowatt hours. That's the ideal storage capacity. It's important to mention that the CHP was only able to run under nominal load. So it was only able to switch on and off. It had no possibility running under part load conditions. We now did some theoretical considerations about the switching cycles of the CHP. As I told, the CHP had a power output, a heating power output of 10 kilowatt, and the maximum heat load of the building was 10 kilowatt too. So under very cold winter conditions, the CHP was running all time long. But under most conditions, the heat load of the building was much lower than 10 kilowatt, though the system has to be switched on and off. And the question now was, how often will the CHP switch on and off? And we have different heat load conditions. Assume first the consumer under low load heat conditions just need a heating load of 1 kilowatt. Though the heat generator produces 10 kilowatt, just 1 kilowatt is used, though the rest 9 kilowatt hours are used to charge the storage tank. To charge a storage tank with a capacity of 47 kilowatt hours with a power of 9 kilowatt hours takes a time of 5.2 hours. The discharging is done with a capacity of just 1 kilowatt, so it will take 47 hours to discharge the storage tank. So altogether we have a period for the whole cycling of 5.2 plus 74. That is a bit more than 52 hours, so that's more than 2 days. So in under theoretical conditions, in that case, the GHP would just have 2.25 days. What's in case of high load conditions? So the consumer needs 9 kilowatt of heating capacity. In that case, the charging is done just with 1 kilowatt, and the charging time takes 47 hours. But the discharging time is now much faster, it's just 5.2 hours. Though the time of a whole cycle is the same, it's 52 hours. The lowest cycle time you get when the consumer needs just half of the power the generator produces. That means the generator produces 10 kilowatt and the consumer needs just 5 kilowatt. Here we have a charging time of 9.4 hours and a discharging time of 9.4 hours too. That means altogether we have a cycle time of round about 19 hours. That's round about one start a day. If we now look to the actual switching cycles of the CHP, we had about 2 to 3 starts during a day. I mean, that's a thing that doesn't drive me nervous, but the operator of that plant, he was not very happy. So if you have short switching cycles, that indicates that you have a lower storage capacity than assumed. The question now is how you can rise the storage capacity. First of all, you can think of using another higher capacity. But I do not know a fluid with a higher specific heat capacity than water. The other thing is you could use a phase change material, but that's another technique. I do not want to talk about it today. The thing most people will do is an extension of the storage mass. That means just building a bigger storage tank or building a second storage tank or something like that. But that doesn't look like a very intelligent solution. Because it doesn't make the system more efficient. And we want a system more efficient, so we looked to the temperature stratification in the storage tank. That means how stable are the temperatures in different layers, how big is the mixing. We looked to the position of the temperature sensors, and we had a look to the switching point for starting, loading and unloading. And at the very beginning, it was not very easy for us, or we had difficulties in overlaying these different problems, as long as my student, Christian Dietrich, had a great idea in demonstrating the whole things in a graphic way. What is shown here in that diagram, on the y-axis you have the high of the storage tank, and that high of the storage tank is plotted versus the temperature, which is here on the x-axis. And the blue and the red line show that temperature over the high of the tank at a certain time. The red one is when the charging is finished, so the generator just stops running, switches off, and the blue line indicates the temperature over the high of the storage tank when the tank is empty. That means that the generator has to be switched on again. And you're going to divide the storage tank in different layers. Here we have 10 layers, so we talked about before that the tank has a capacity of 1,000 liters. So in that case, every layer has a capacity of 100 liters. And if you are now calculating the specific capacity of each layer, it's the mass of each layer multiplied with the specific heat capacity of the water, multiplied with the temperature difference of the layer from the point when the generator is switched on and the generator is switched off. And of course, you take the temperatures in the middle of each layer. And then the total capacity of the whole tank is the sum of each layer. That means the area, the exceeded area in that diagram, the exceeded area from the red to the blue line, in the amount of energy that is stored inside the tank. So it is very important for you to know the temperature distribution in the storage tank. And to get a better understanding what is happening in there, we involved 3 idealized heat storage tanks. On the left-hand side, you see an ideal mixed tank. In an ideal mixed tank, the temperature in the tank is everywhere the same, so you mix it ideal. In case charging this tank, you have the temperature curve, which is vertical. And charging the tank, that vertical temperature line goes to the right, and discharging the tank, the vertical temperature line goes to the left. And the exceeding of that line is again showing how much energy can be stored inside. The next ideal tank is the ideal stratified tank. In that tank we just have 2 zones, a high temperature zone and a low temperature zone. And if you charge the tank, the line between the high temperature and the low temperature goes down, and if you discharge the tank, the line goes up. And here again, the exceeded area shows you how much energy can be stored. These 2 storage tanks are very idealized, so you will never get them in reality. And to make the thing a little more realistic, we also introduced a so-called linear stratified tank. Here we have a linear connection between the lower temperature and the upper temperature. And in the tank, this line comes down, discharging the line comes up again. So, and here again, the exceeded area of this line is the storage capacity you can store in the tank. And what you have to do now is to make the tank as big as possible. What we are doing, we put these ideal tanks into our hydraulic scheme. That's done here. So the question is, that's the first tank, that's the ideal mixed tank. In the ideal mixed tank, I just repeat, the temperature is everywhere the same. The vertical temperature line here is going to the right loading and going to the left unloading. The question is to which temperature you can charge the tank or load the tank. Theoretically, you can load it to a maximum temperature of 90 degrees. But we figured out that in that constellation, that point was set to 80 degrees. So the storage tank, it was charged with 90 degrees water, everything was mixed, and the charging goes up to a temperature of 80 degrees. And at 80 degrees, that was the set point of the sensor, and at 80 degrees, the sensor switched off the generator. And now, the unloading or the discharging of the tank started. And the question is, how far discharge this storage tank? The return flow temperature is 50 degrees. So from a theoretical point of view, you could unload this tank at 50 degrees. But be careful, your consumer needs a temperature of 70 degrees. So as soon as you drop the 70 degrees, you have not enough power at your radiators. For that reason, you are not able to discharge that storage tank to 50 degrees. No, you have to stop by 70 degrees. And you see now, this vertical line just moves from 70 to 80 and from 80 to 70. And the area, the exceeded area, shows you the energy that can be stored inside the tank. And you are now seeing that you have not a temperature difference of 40 degrees, as we assumed before. You just have a temperature difference of 10 degrees. That means that the storage capacity is just 1/4 of that what we expect. So, there was one more question. How many sensors, temperature sensors, do you need to tell the CHP or the generator to switch on and off? And where are you going to place that sensor? All thinking? Anyone an idea?
Two.
You need two sensors?
Yeah.
And where do you place them?
Up and down.
Up and down. I gave a question to you. Why do you need two sensors if the temperature is everywhere the same? They will both show. That's an ideal mixed tank. Yeah? You're not totally wrong for reality. For these ideal mixed tank, the temperature is everywhere the same, so you need just one sensor. And where do you place the sensor? It doesn't matter at all because the temperature is everywhere the same, as long as it is an ideal mixed tank. So now we come to the next examples. Here we have an ideal stratified tank. In the ideal stratified tank, we have two areas, the warm area at the top and the cold area at the bottom. And if we charge the tank, that horizontal line goes down, and if we discharge it, the horizontal line goes up. And the exceeded area is responsible for the energy we can store in the tank. And now I ask you the same question. How many sensors you need, and where would you locate these sensors? And yeah, now your question is right. How many you need? Two of them. And where are you going to locate them?
Up and down.
Yes, and I think you could do it much better than it is shown here. The lower sensor should be as low as possible, and the upper sensor should be as far at the top as possible, because then you get a large area you exceed. The silly thing is that in practice we have many storage tank systems running just with one sensor. And it wouldn't be a problem to install more sensors at the thermal storage tank, but the problem very often is the generator. The generator, in many cases, especially small generators, have just an inlet for one sensor. So we run big storage systems with stratified tank having just one sensor. And what happens then? The tank is not fully charged and discharged. That line goes just across the sensor a little bit. Huh? The next question is, what should be the set point of the sensor? That means the set point at what temperature should the charging be stopped or the discharging be started. In case of an ideal stratified tank, it doesn't make much difference. Because we have just two temperature zones, 90 degrees at the upper part and 50 degrees in that case of the lower part. And as long as the sensor, the signal, is something in between, it doesn't make a difference. Yes, you can say that sensor, okay, I should switch off the generation if 60 degrees is reached here or 70 degrees is reached here. That doesn't make any difference because we just have 90 and 50 degrees for it. But that is just is independent of the temperature. That is just relevant for an ideal stratified storage tank. The reality is better described by a linear stratified storage tank. In a linear stratified storage tank, we have these ancient lines going up and down. And the question now is how many sensors we need to control the system, and what are or what should be the set points of the sensors. So you always want to have storage capacity as high as possible. High storage capacity means that the exceeded area should be as large as possible. What do you have to do to get a large exceeded area by the lines here? How many sensors you need? T2, very close to the bottom, and the other one very close to the top. And here the question is the set point relevant for the storage capacity? Yes, it definitely is. You see, if you have, for example, if you say if the sensor T2 is responsible for switching off the generator, if this switch off is set to a temperature of 70 degrees, then the charging is stopped when the line is here. If the sensor is set to 80 degrees, it stops here. If the sensor sets to 90 degrees, the charging is done up to here. So in that case of a linear stratified storage tank, the positioning of the sensors and the setting of the switch on and off point are responsible or have an influence on the real storage capacity of the storage tank. So, what we did next, we looked at our real system. So we inserted 8 sensors to our storage tank, and we monitored the whole thing. And that is a temperature profile we measured at our realistic tank. And out of that area, we calculated the storage capacity to 17 kilowatt hour. If you go back to the theoretical ideal storage capacity, which was just the mass of the total mass of the storage multiplied with a specific heat capacity, multiplied with the charging temperature and the discharging temperature, we would get a theoretical storage capacity of 59 kilowatt hour. The reality shows us just the capacity of 17 kilowatt hours. So there's a big difference in between which can be optimized. We just did one thing here. This project was financed by a company which produces some special valves, some so-called four-way valves, and for that reason we did exactly looked at these things more closely. These four-way valves, they have 3 inlets and they have 1 outlet, and they can mix we need a temperature at the consumer of 70 degrees, and as long as we have in the middle of the storage tank a temperature about 70 degrees, that valve is mixing the return temperature here at the bottom side with the temperature in the middle of the tank to 70 degrees. The colder the tank gets in the middle, the less return water is mixed. As soon as the temperature in the middle of the tank drops below 70 degrees, the wave takes the temperature from the upper part of the tank and mixes the 90 degrees water to the middle tank water. And in so far you get 2 zones of the storage tank. And if you look to the temperature profile we're getting now, we see big difference to the first one. So that was the storage capacity in the beginning. Then we changed the hydraulic system with these 4-way valves, and we got this solution. And you see the storage capacity was raised from 17 kilowatt hours to 27.4 kilowatt hours. That is a factor of 1.6. What would be your next idea to increase the storage capacity of that situation? The sensors for switching on and off are indicated by the blue and the red color. So the sensor for switching on is the sensor T3, and the sensor for switching on is T3, and the sensor for switching off is T6, and the sensor T6 is located here. Is that the very bottom of the storage tank? Definitely not, and you see it very clearly in that slide. All that lower part here isn't charged at all. So it would be much better solution putting that sensor T6 to the position T8, and then that line comes down to that part, and that gives you another increase of storage capacity of about 1.5. But if we make a comparison of the running time of the CHP unit due to the hydraulic changeover, we had, just by insert this four-way valve, we had 2 to 3 starts a day before that changeover, and we had just 1 starting after the changeover. So it was a reduction of starts by the factor of 2 to 3. Afterwards, we got the idea to define the storage utility level. And the storage utility level is defined by the effective storage capacity divided by the theoretical storage capacity. And at the very beginning, we had a storage utility level of 17 kilowatt hours divided by 59 kilowatt hours, which is lower than 30%. Introducing that four-way valve, we raised the storage utility level to 46%, and changing the sensors for the positioning of the sensors for switching on and off, we could raise the storage utility level to more than 70%. That means with very easy changes, without rising the size of the storage tank, we were able to improve the capacity of the storage tank by more than 50% to double capacity. And in the past, I did more and more studies about the skill level in practice, and I figured out that in reality, the storage facility level varies in a very wide range. It varies between 10% and 19%. And I'm always asked, and also by people in practice, what is the storage tank we need? I can't give them an answer, because if the storage utility level varies in the range of 10, how should you dimension? But it's almost impossible. So there's work that has been done in these fields. I hope you have some questions to make it more clear, or is everything so far?
The T6 temperature meter, you didn't have it in the bottom.
No.
Why?
But the reason therefore,
Yes.
we were limited in time. So the first thing is we started with this boundary condition. It was located at that position, yeah. And as I mentioned, the research work was financed by a company which are producing these four-way valves, and they wanted to figure out how much they can increase the capacity using their valves. And if you make testing, you should always only change one dimension at one time and not change too many dimensions at the same time. Otherwise, you do not know which effect was responsible for the new results. And for that reason, we changed the valve first, and then we were running out of time and we had no possibilities to change the position of the temperature sensor. So that was just a theoretical investigation which was done. afterwards.
Can you please tell us some practical applications where these new types of
They can be used, for example, to get a better efficiency in storage tank. Another very common use of these valves is, there are many applications, but a very common situation is if you have a combined heating system with radiators and floor heating systems. So you can run the radiators and the floor heating systems in series. So the return flow of the radiators is the supply flow of the floor heating system. If you do it a conventional way and someone turns off your radiators, the floor heating system do not get any water. And with these four-way valves, you can install it in a way, it's a bit complicated, but you can install it in a way that you can operate the radiators and the floor heating systems in series as well as parallel. So it works always. If you work it in series, you get a low return flow. But if one of these heaters is not needed, you also can operate them separately.
Could you please give an example also outside residential buildings?
That's not only for residential buildings, that's also for commercial building. You may have a floor heating system and some air heating combined. You can always combine it if you have different temperature levels. In all cases, you operate with more than one temperature levels, you can use these valves. That's a very small producer. It's a factory Baunach from Germany. But you could also use, let's say, you can either use that four-way valves, but these four-way valves can also be imitated by two three-way valves. So you can find other ways to do exactly that construction. Okay, further questions? Not at the moment. Okay, and I'm going to change to the next presentation. So that presentation is titled "The Sizing of Energy Storage for Zero Energy Building, or is it perfect, the enemy of the good?" That subtitle you will understand, or you should understand at the end of the presentation. The first way of using solar energy for heating demand was a passive one, just by windows. Here, the mass of the building acts as an energy storage. With the beginning of the 1980s, a lot of active solar thermal heating system has been installed, at least in Germany, Switzerland, and Austria, to provide domestic warm water and to support space heating. Here, the storage tank was sized in a way to provide a capacity for 1 to a few days. With the beginning of the new millennium, the number and the capacity of installed PV systems in Germany was forced by a new Energy Feed-in Act. To push that new PV technology, a feed-in tariff was paid to the producers of PV electricity, which was much higher than the prices charged to the end consumer. In the very beginning in 2000, the feed-in tariff for electricity in Germany was about 50 cents per kilowatt hour, 50. At that time, the purchase price for electricity for the end consumer was about 15 cents per kilowatt hour, 1.5. That means at that time, nobody thought about using their own PV electricity. Everything was sold into the grid. I built a PV system on my house in 2001, and I get 45 cents per kilowatt hour, and that price is guaranteed for a period of 20 years. So at the moment I'm getting 45 cents per kilowatt hour. I do not use that electricity. I sell it into the grid and buy the electricity much cheaper from the grid. Now at that time nobody thought about using their own PV electricity. Everything was sold into the grid. But as the guaranteed price was dropping down by time and the prices charged to the end consumer rise by time, grid parity was achieved in 2012. And from that point on, building operators tended to consume their own PV electricity rather than feeding it into the grid. That leads to a strong grid relief. Only recently, producers of PV electricity have started to consider the addition of on-site electricity storage on their system, as the guaranteed price dropped down to 13 cents per kilowatt hours, whereas the purchase price for electricity rises up to 29 cents per kilowatt hour. So electricity in Germany, the price for electricity in Germany is much higher than the price for electricity here in Finland. I think you just told it's about 12 or 13 cents per kilowatt hours. So our prices are 2.5 times higher than the prices are here. Yeah? Okay, in the future, not only the number of PV systems which are necessary for zero energy building will grow, but also the importance of electric heating, either by heat pumps or by direct electric heating. Against the background that the solar supply is mainly during summer, but high heating demand is required during winter time, the network load will rise. Compared to a reference building with a good building envelope and a gas condensing boiler, a zero energy building equipped with a PV roof and a monoenergetic bivalent heat pump system will lead to an additional feed-in of about 6 kilowatt to the grid during summertime and an additional power consumption during wintertime of another 6 kilowatt. That means as long as only a minority of people are using these zero energy buildings, the energy saving aspects can be placed in the foreground. But a large number using these buildings will create big grid problems. And to limit that problems, energy storage capacities have to be installed on site. And this investigation is dealing with the sizing of both electrical and thermal energy storage under economic aspects. From the viewpoint of a building operator, the public grid can be seen as an external storage. And the costs for using this external storage is the price difference between the purchase price and the feed-in tariff. As I told before, I am selling my PV electricity still now for 45 cents to the grid, and I buy the electricity for 29 cents a kilowatt hour. That means I have negative storage prices, and for that reason I won't use my own electricity. But if you install a PV system today, you just get a feed-in tariff of 13 cents per kilowatt hour. That means you have storage costs of around about 16 cents per kilowatt hour. The specific, yes, and these specific costs for using the public grid as a storage can be used as a benchmark for the on-site battery systems. In a static economic analysis, one would divide the investment costs of a battery system, which are nowadays around 700 euros per kilowatt hour capacity, electric capacity, by the number of maximum life cycles, charging cycles, which are around 7,000 nowadays. Though you get specific investment cost of the battery system of round about 10 cents per kilowatt hours. Although this specific storage cost of the battery system seems much lower than using the external grid, caution is needed. In an advanced economic analysis, one also has to consider the lifetime of a battery. And the lifetime of a battery is limited by two reasons. First reason is the time, for example, 20 years. After 20 years, all the plastic material of the battery will break down. Maybe it can be 25 years, so we can change the numbers a little bit, but to get an understanding, we will just fix it to 20 years now. Though it is fixed, for example, to 20 years, and it is limited by a maximum full charging cycles, for example, 7,000 here. What is achieved first is responsible for the death of the battery. Imagine a battery as a sum of battery cells charged and discharged after the principle first in, first out. Then the first cell on the left-hand side passes through much more charging cycles than the last cell on the right-hand side during a given period of time. Since the economic of each battery is influenced by the real charging cycle of each individual cell, the term of full charging cycle of the last battery extension is introduced here. That means how often is that last battery cell charged during lifetime. In order to assess the economic viability of the battery capacity. As the charging cycle of the whole battery, and especially the charging cycle of the last battery extension, are decreasing with a growing storage capacity, the specific storage costs are growing with larger batteries too. The research question now is, how many changes does each battery cell experience? And as this idea can be transferred to thermal storage, the research question can be generalized. How often is each storage capacity charged during lifetime? To answer this question, we adapted a very powerful simulation tool written in MATLAB Simulink, based on a very detailed building and plant model, which was used for a previous investigation on solar-driven heat pumps to that problem. And the simulated building, or the simulated domestic building, had a living area here of about 150 square meter, and it was equipped with a 6 kilowatt peak PV system. The electrical household consumption was about 4,300 kilowatt hours of electricity a year, and the total heating demand was about 3,800 kilowatt hours a year for domestic warm water and heating applications. In the first simulation, the heat demand was covered by the condensing boiler, and only the capacity of the battery was varied. In the second series of simulation, the capacity of the battery was fixed to 10 kilowatt hours, and a heat pump system with different size of storage tank was involved to the system. And it is important to notice that this PV system was only driven with a surplus, the heat pump system, was only driven with a surplus of PV electricity. So there was no electricity taken from the grid to drive the heat pump. The heat pump was only driven with a surplus of PV electricity, and if there was not enough PV electricity, then the gas boiler was used for the heating demand. With a 6 kilowatt peak PV system, you can generate about 6,500 kilowatt hours of electricity in Germany a year. This diagram shows the result, or summarizes some results. It shows the PV own energy consumption and the grid independent ratio over the battery capacity. Without any battery, we have about 1,300 kilowatt hours of PV own energy consumption, and that is a grid independent ratio of about 30%. Both values can be raised by adding a battery to the system, and with a small battery capacity of about 5 kilowatt hours, we can double those values. With 5 kilowatt hours capacity, we can reach a PV own energy consumption of about 2,600 kilowatt hours and getting a grid independent ratio of about 60%. A further increase in battery capacity only results in a moderate improvement. An increase exceeding the capacity of 20 kilowatt hours leads only to a marginal improvement or to a marginal success. The reason, therefore, can be seen in the next diagram. And the reason is the drop of full charging cycles, which are indicated by the blue line here. So the blue line indicates the average full charging cycle of the whole battery system. If you have a small battery with a capacity just of 1 kilowatt hour, this battery is charged every day, or almost every day, and you get here 350 charging cycles a year. That means during lifetime of 20 years you get about 7,000 charging cycles. But if you increase your battery capacity, the full charging cycles go down. For example, with a battery capacity of 10 kilowatt hours, you just get about 180 full charging cycles a year. With a capacity of 100 kilowatt hours, you just get 20 full charging cycles. And with a battery capacity of 1,000 kilowatt hours, which is necessary for reach grid independence, you just get about 3 full charging cycles a year. That means 60 full charging cycles during lifetime. The red line shows the specific costs for the battery, and this specific cost for the battery you get if you divide the investment cost by the real number of charging cycles. And the orange and the green line, they indicate the reference using the external grid as an energy storage for different feed-in tariffs. So the orange line indicates the actual feed-in tariff of 13 cents per kilowatt hour, and the green line indicates a feed-in tariff of 4 cents per kilowatt hour. That is what we expect for the nearer future. And if you assume that in this house, a battery system up to a size of around 7 to 8 kilowatt hours can operate under economic conditions. In the near future, if the feed-in tariff drops, you also can use larger batteries with a size of about 20 kilowatt hours and can operate under economic conditions. Larger battery sizes will never be economically. And imagine you have a battery of 1,000 kilowatt hours, which is just charged 60 times during lifetime. That can't be economically. So depending on the number of, depending on the feed-in tariff, between 155 to 220 full charging cycles of each battery cell are necessary to operate under economic conditions. So it doesn't make sense to build the batteries too large. In the second series of simulation, the capacity of the battery was fixed to 10 kilowatt hours, and a heat pump was added to the system. And the size of the thermal storage tank was increased in steps from 300 to 50,000 liters. So at the beginning, a very small tank, just 300 liters, up to 50,000 liters. The results are summarized in this table. By adding a heat pump to the system, the PV own energy consumption grows by 20% to 2,700 kilowatt hours, using only a small storage tank of 300 liters. Although the gas consumption decreases at the same time by almost 50% from 4,100 to 2,100 kilowatt hours a year. Expanding the storage tank size increases the PV own energy consumption. With a 50,000 liter storage tank, a PV own energy consumption there of almost 85% were reached, which means that most of the PV electricity can be used on site. But what looks great at the first glance does not always provide an advantage, because the goal is not to blandish key figures, but to reduce the gas and the electricity consumption needed from the grid. While the electricity required from the grid is constant in case of ideal operating control system, the consumption of the gas boiler is minimal at a storage size of 2,000 liters. So that's a bit wondering. Normally you would assume the larger the storage tank, the lower the gas you need from the grid. The reason, or that can be explained by looking to the thermal input. The energy input to the storage tank rises with an increasing storage tank. But due to higher losses of the larger tanks, the energy output of the storage tank is a maximum at a size of 2,000 liters. So storage tanks larger than 2,000 liters do not act as a storage tank only, but also as an additional consumer. Further on, the large storage capacities can not be fully utilized as they are not completely charged during summer. This is due to limited capacity of the heat pump. Furthermore, the increase in PV-owned electricity consumption is not necessarily an advantage. It is not a benefit to convert a surplus of PV electricity into thermal losses of the storage tank. That's just to blandish key figures. So let's come to the conclusions. The major problem of the future won't be to generate enough renewable energy on an annual basis, but to match the power generation and the consumption at any time of the year. Running seasonal storage under economic conditions that guarantees 100% grid independence is not efficient today. It's almost impossible. Against this background, the use of short-term storage must be spread to a large extent to reduce the CO2 emissions and to stabilize the electric grid during day cycle. In order to release the grid load on very cold winter days, a shutdown of all electric heaters must be forced, and that for electric heaters as well as for heat pump whenever it is needed. And you should have in mind, in the future, we would like to use electricity also for driving our cars, so that will create some problem. But if you force a shutdown, that requires a bivalent heating system which can be driven with an energy carrier you can easily storage. That can be wood on the countryside, but that could also be natural gas within cities. In this way, the demands of CO2 savings and grid stabilization can be reached most economically in a short term. We know exactly that that won't be the final solution, but it's our firm conviction that striving for this intermediate solution will be more helpful to meet the climate goals than losing one's labor and searching for the ideal solution while time is running short. Thank you very much. Do you have questions to that topic? And you can transfer these ideas to many things. I just told you that we are also talking about change in mobility. We are going to we plan to do more electric mobility. And I just have a project dealing with electric local buses. And there we have a real big problem. And the problem is these buses, they have to travel a distance of about 300 kilometers a day. But we have to design the battery capacity for 600 kilometers. Do you have an idea? The background is that during very cold winter days, and also in Germany, the temperatures can drop down to minus 20 degrees, the same as we had here today, but that happens, let's say, every 5 to 10 years, and just for a few days. But for that few days, we have to double the size of the batteries because we have to do heating in the transportation system. The other idea is to say, okay, we are powering the electric motor by, or the motor by electricity, but we are going to do the heating by gas or oil, which would be much more efficient. We have a saying in Germany, the most stupid things you can do with electricity is heating. And now we start heating with electricity we have to store in batteries. So that's really incredible. So in a first step, I mean, it can be that we are doing so in a 20 or 30 year time, but the first step should be turn the movement to electricity, but keep the heating with gas or oil. And I mean, just to double the capacity of the batteries, that makes a bus about 5 tons more heavy. And this 5 tons of battery has to be transported all year round. That also costs some additional energy. Huh? Question?
No problem. I'm just wondering how I can load those curtains, but I cannot find. That is my question. How can I really?
Technical problems, yes.
So that is my view. Okay, but you can continue.
Okay.
Ah.
Okay, let's come to my last presentation, that the optimized integration of storage tanks, especially in heat pump system, but it also can be transferred to cold water chiller system. It has no influence on boiler systems or something like that. Heat pumps are becoming more and more popular, I think, in the whole of Europe. We have a large growing of the installed numbers of heat pumps during the past years, especially for heating low energy buildings. Especially. In Germany, air-to-air heat pumps are not very common. We use air-to-water or ground-to-water or groundwater-to-water heat pump systems. That means we have a hydraulic water system inside the building distributing the heat to the different rooms. And in this hydraulic system, you can easily integrate a storage tank. And this storage tank is used to reduce the start-up of the compressor of the heat pump and to adapt the heat capacity of the heat pump to the heat demand of the building. And in the future, these storage tanks may also be used to use low-rate electricity. That means if the electricity is cheap, you run your heat pump system, store the heat in a storage tank, and if the electricity is expensive, you can discharge your storage tank instead of running the heat pump at that time. In general, heat pumps have a good reputation in being very energy efficient. but the daily practice quite often looks very different. And the main reason therefore is that the temperature difference between evaporation at the heat source and condensation at the heat sink is much higher than proposed. And the efficiency of a heat pump is very much depending on the temperature difference between evaporation and condensation. This slide shows you the real efficiency depending on the temperature difference of evaporation and condensation. And you can say an increase of the degree temperature difference, of an increase of 1 degree of the temperature difference decreases an efficiency by 2.5 to 4%. So in average, I say, if the temperature difference rises by 1 degree, the efficiency goes down by 3%. That means if you have a 10 degree higher temperature difference, your efficiency goes down by 30%. That's quite much, and that should make you think about it. Okay, to guarantee high efficiency on heat pump, on small heat pump systems, which are not equipped with the monitoring systems, we developed a 24-hour monitoring kit. In the past, it was around 2010, to monitor heat pump systems for 24 hours and figure out the problems they have and reduce or solve these problems. And during our tests, testing our monitoring kit, we figured out that at all heat pump systems, we have a drop of supply temperature from the heat pump to the consumer in the range of 0.3 to 7.2 Kelvin. That means the water left the heat pump with a temperature 7 degrees higher than the water arrived the consumer. And I will point it out here, the temperature loss was not due to energy losses of bad insulated piping, it was due to other problems. And that was the reason for our further investigations. The problem is, if you have a required temperature level at the floor heating of 35 degrees, for example, and you have a supply temperature loss of 7 degrees, then you have to drive your heat pump with a supply temperature 7 degrees higher, that means 42 degrees, and that leads to an efficiency increase of 7 multiplied with 3 of about 20%, which is quite high. And for that reason, investigation for an optimized integration of storage tank are discussed in this presentation. First of all, we did a literature review and we were searching for reasons for this temperature decrease, but we didn't find anything. We also found no recommended ways of integrating storage tanks and heat pumps in hydraulic systems to reach the highest efficiency. Though we had a look to the most common ways of integrating heat pumps and storage tank in these energy systems, and there are two, or at the end 4, very common ways. The one is a parallel hydraulic integration shown at the left-hand side. Here the storage tank is parallel to the heat pump and the consumer. In that way it is connected by the so-called 2-pipe connections. We also have the 4-pipe connections. There we have 2 inlets and 2 outlets. And on the right-hand side, you have a serial hydraulic integration in the return pipe. To integrate the storage tank in the return pipe has the advantage it is operating on a lower temperature level and so have less losses than installing it in the supply line. This slide shows a typical temperature profile of the outlet temperature of the heat pump and the supply temperature at the consumer, if the storage tank is in series. So let's go backwards. So we are talking about the right situation here. Under most conditions, the power outlet of the heat pump is larger than the heat demand used of the building. Insofar as long as the heat pump is running, the system gets warmer and warmer and the temperature rises. And the temperature that the red dot line is the temperature outlet at the heat pump, is shown by the red dot line, and the green line is the supply temperature of the consumer. And I think that's what you expected. If we are neglecting all the pipe losses, the heat, or the temperature, not the heat, the temperature leaving the heat pump is the same as the temperature arriving at the consumer. Yes? Although both temperature profiles are identical, their mean value differ due to different operation periods of the heat pump and the consumer. If we look to the heat pump, the mean temperature of the heat pump is indicated here. It's the mean temperature over the operation period of the heat pump. But if we look to the mean temperature at the consumer, it is lower, because that's the mean temperature arriving at the consumer. And that temperature difference is named the drop of mean temperature. And that is depending on many things. The study of this drop of mean temperature is a central concern of this research. Our field test monitoring done in 2010 gave some first impression of the drop of mean temperature, which was between 0.3 and 7.2 Kelvin. In order to obtain more precise statement free of undefined boundary conditions, a laboratory test facility was set up. And in this test facility, the heat pump was simulated by some electric heater, which was able to give a heating capacity from 3 up to 19 kilowatt. That electric heater was able to operate on a constant temperature mode. That means that the outlet temperature was constant, or it was able to run under constant power mode. That means if the inlet temperature rises, also the outlet temperature rises. The consumer was in water-to-air heat exchanger with a 7-speed van to control the heating load. And then we put in a storage tank with a volume of 200 liters, and that storage tank was equipped with equal space temperature sensors to see what is the temperature profile over the storage tank. And we also measured the mass flow rate in the generator loop and in the consumer loop. So that has been our practical investigations. We also did some theoretical investigations that was done by a colleague of mine, and he simulated the model, and he separated it into 3 parts. One part was the heat pump, the other part was the model consumer. It is called model consumer, but here the bypass, which is necessary in case of serial integration, was integrated. and the storage tank. And to keep the model quite simple, we neglected the connection pipes, we had no dissipative losses, and the mass flow was piecewise constant. Though the only time-independent correlations has been the temperatures after the heat pump, after the model consumer, and after the storage tank. And we were able to calculate that drop of mean temperature without simulation. We were able to calculate it on an analytic way. The question now was in which way that you have to calculate the drop of mean temperature. You have to know, is the storage tank integrated in serial or parallel? And do you have a temperature mixing in the tank, or do you have a strong stratification? And to know what's happening in the tank, we'll look at our temperature profile. Sorry, here we get. And that is a temperature profile for parallel tank integrations. The different colors indicate the temperature at a given location over the time. The red line is at the very top and the dark blue line is at the very bottom. And here you can see a quite good stratifying for the charging procedure and a very good stratification for the discharging situation in case of parallel tank integration. In case of serial tank integration, we have seen difference depending on the mass flow. So if the mass flow over the heat pump was quite low, we had a very good stratification during charging, and we had an almost ideal mixing during discharging procedure. If we raised up the mass flow at the heat pump, we had an almost ideal mixing during charging as well as during discharging time. So let's come to the results. Have in mind, the higher the DOMT, the lower the efficiency of the system, or the higher the efficiency losses. So in case of parallel integration, our measured drop of mean temperature was quite low. It was just between 0.2 and 0.4 degrees Celsius. So that's very low. In case of serial tank integration, the drop of mean temperature was much higher. It varied between 2.1 and 10.5 degrees Celsius. Have in mind, 1 degree higher temperature losses means 3% lower efficiency. So if you have temperature losses of 10 degrees, that means 30% efficiency losses. That's really amazing. Now we compared our measured with our calculated results. In case of parallel tank integration, the measured drop of mean temperature fit very well with the calculated drop of mean temperature, so that's almost perfect. In case of serial tank integration, the measured value was always in the middle of the calculated, depending which model we used. If we used mixed storage model or stratified storage model. And the reason is quite clear. We had both. Sometimes we had the mixing mode, sometimes we had the stratified situation. So that's also fitting very well. So what are the conclusions? We have a very good agreement between the theory and the practice. Of course, we could make a better theory, but that's getting quite complicated for calculating them. The parallel tank integration should be clearly preferenced. But there's one thing necessary I explained before. Parallel tank integration is operating with a stratified tank, and a stratified tank needs 2 sensors to start and stop charging and discharging. In practice, many of these systems just are operated just with one sensor, and that's not working at all. So two temperature sensors are needed for the parallel integration of a stratified tank, and problems and results can be transferred to cold water chiller systems. That's what I told you at the very beginning. And these investigations are not finished, so we are looking for more sponsors to develop a totally new control strategy. But what we figured out meanwhile is that it is also possible to get a negative drop of mean temperature. That really sounds silly at the very beginning. Negative drop of mean temperature means that the water arriving at the consumer is warmer than it left the heat pump. That sounds at the first way as a perpetuum mobile second class, which is impossible. But the thing is, it is not the temperature at a certain time, it's the mean temperature over a given period of time, and the period of the operating of the heat pump is different than the period of operating the consumer. How to get that negative drop of mean temperature? Assume a heat pump running here, and assume you have a mixing. Now you charge your storage tank in a mixed mode. For example, you have a very high mass flow in the heat pump cycle. Then the temperature here is just raised in very small step, and you are going to charge the tank in a mixed mode. So the temperature rises from the point where you switch on the heat pump to the point where you switch off the heat pump, and the middle temperature is indicated here. If you are now going to discharge the tank as a stratified tank, if you have a low flowing rate in the consumer loop, you have a constant temperature as a supply temperature until the storage tank is empty. And then the temperature drops down immediately. So the temperature at the consumer is in the beginning, it's here until the heat pump stops, and then you have a constant temperature level until the tank is empty. So the average temperature at the consumer is about here. And its average temperature at the consumer is higher at the average temperature at the heat pump during running time. And we reached in our test facility negative drop of mean temperatures up to 5 degrees. So that means from the best case, drop of mean temperature of -5 degrees to the worst case, temperature drop of mean temperature by 10 degrees, there's 15 degrees temperature different in between, and 15 degrees temperature different means about 45% of efficiency. I mean, I'm sure that's not the way, or that's not, you can't improve it by that range in any way, but it just showing up, there is a big possibility, and if you get an improvement in reality, which saves about half, that's still more than 20% of saving, just by thinking about integration, hydraulic integration of the storage tank and the heat pump and the control facility. So that all doesn't mean higher costs of investment. That's just thinking about how can you do it more intelligent. Thank you very much for your attention. So, any question to that topic? You're waiting for the ice hockey game?
Okay.
Okay.